Hello students, from this lecture we are introducing you with a new topic, that is Turing machines. So in this lecture we will be covering the formal definition and formal model of Turing machine, and all these concepts we will be understanding with the help of an example. Turing machines are basically used for the type 0 languages. So let's start the lecture with a brief introduction of type 0 language and the formal definition and formal model of the Turing machine. So here we have the Chomsky hierarchy, where the type 0 is at the top level, means the first level is type 0 language, or we can say that type 0 is superset of all other languages. So type 0's languages are also known as recursively enumerable, phrase structured and unrestricted form of the grammar, and these languages are recognized by the Turing machine. Second thing to notice here is, as the type 0 is the superset of all other languages, all other form of the language, so type 0 can recognize regular languages, can recognize context free languages, and also can recognize the context sensitive languages. So type 0 language can accept any other form of language, means they can be used for any other language. Means for a question, if we can easily construct DFA, NFA or a PDA, so you can also construct Turing machine. So Turing machine can be the solution for any other language, right? So let's see, discuss some of the features of the Turing machine. So the concept is suggested by Mr. Alan Turing in 1936, and all the type 0 or recursively enumerable languages are defined using the Turing machine. So Turing machine is used to define all the type 0 languages. Next, it can support read and write operations. So unlike DFA, NFA, we can perform the write operation with the input tape. So we are having input tape like any other formal model, but here the difference is this, means we can perform the write operation for the input tape as well. Okay, so as in the DFA, NFA, we can only read the input from the tape. Here we can also write the output on the tape. So Turing machine is capable of performing the recognition as well as the computation. So here the recognition is also done by DFA, NFA and PDAs. So all those concepts are same as the DFA, NFA and PDA, but here the difference comes as computation, means we can also perform the computation with the Turing machine. So Turing machine, we can say that, is capable of generating the output for the given input. Okay, next thing, unlike DFA, NFA, we can move in any direction, any number of time for the input string. So here, as in DFA, either we can move from left to right or right to left. Okay, so we are restricted in one direction only, but in case of Turing machine, we can move from left to right, then from right to left, or we can move in any direction, any number of times. So these freedoms or unrestrictions are given with the Turing machine. So you can move with any direction, you can implement any logic with the help of Turing machine. So let's start with the formal model of the Turing machine with an example. So here we are considering a problem of converting all the lowercase letters to uppercase letters, and the symbols for the inputs we are considering as A and B. So input symbols here are A and B, means input string will be the combination of A's and B's, lowercase A's and B's. Now the tape symbol we are taking here as AB, lowercase ab, and the capital A and B. Okay, because here we are saying that you can compare these tape symbol with the output symbols of Millet-Murray machine. Like here we are having input symbols as A and B. So lowercase a and b are taken as the input symbol, and the capital A and B are the output symbols, right? As in the Turing machine, we will be having output on the tape and also input on the tape. So we will be considering both set means combination of input symbol and the output symbols as a tape symbol. So here the tape symbols are defined as this. So lowercase a and b and capital A and B. So here we are not defining them as output symbol, we are defining them as tape symbol. So input set, input symbol and the output symbol, or whatever symbol we are using for the computation and for output generation will be considered as the tape symbols, including input symbols. So now for this problem we have converted these strings, mean these symbols of the string are already converted to the capital letters. Now we are left with only two symbols to be read as B and A. Now from the finite control, so here finite control are representing states. So here we are on a particular state, and from this state we are reading the symbol B. Okay, and we have to convert this B to capital B, and next symbol to be read is from the right of it. Okay, so we are moving from left to right for this particular question, as we are not requiring to move in right to left direction, or you can follow any direction, means we need not to repeat the string symbols. Okay, once we have read the symbol and converted it to the capital corresponding capital letter, then we can read the next symbol, we can work with next symbol. So here we just need one move from left to right or right to left to convert the complete string to the output symbols. Okay, so here we have just converted this lowercase b to capital B, and now we are moving, or the state we are changing to read the next symbol, and now we will be converting this symbol to the capital A. So next state will be this, we have converted this to capital B. Now the finite control is pointing to the next symbol as A. Now we have to convert this to capital A as this, and now the tape head, or we can say that the finite control is pointing to a blank symbol. Here these are representing the blanks. Okay, so if there is nothing on the tape, we are having the blank symbol. So now the tape head is pointing to this blank symbol, and these blank symbols are not considered under the tape symbol. So these blank symbols are default for any tape. So before any input symbol and after any input symbol, we are having blank symbols on the tape. So in some books you will find this notation for the blank symbol or a hash for the blank symbol, but here we are using this symbol to represent the blank. You can use any notation. So here after the end of the input, we are, once the tape head is pointing to a blank symbol, that means we are in a position where we have converted the input symbol to the capital letters, and the input is ended now. So now we are at the last, we have already read the last symbol and we are at the blank symbol. Okay, so this state means now the string must be accepted and the remaining symbol on the tape are considered as the output symbols. Okay, so after reading the input and converting all the input symbol to the capital letter, now the tape symbols are representing the output. Okay, and we have performed the required computation. Now output symbols are these, and now the tape head is pointing to the blank symbol. So if there is nothing in the tape, we are having the blank symbol. So here the blank is representing the end of the string. So here we must move to the final state like DFA, NFA or the PDAs, but here we are representing the final state as a halt state. So where, okay, so by moving to the halt state, we mean that the machine is now in inactive state. So the machine will not perform any other computation, and now the machine is in halt state, means the machine has stopped its working, and now we can give the output, read the output, and can declare acceptance or rejection. Now this halt state is very much equivalent to the final state of DFA, NFA, PDA. So here the machine can be in two states like this, active state and the inactive state. So when the machine is in active state, we can move from left to right or right to left, means we can have any type of movement and we can perform any transitions. Okay, now if the machine is in inactive state, that means we are at one of the halt state. So machine will be having a static move, means now machine cannot move to left or right or cannot read any symbol and cannot perform any computation. So the machine will be in inactive state and that state will be represented by the static. And if we have to read the next symbol from the left, then we will be having a left move. If we have to read the next symbol from the right, then we will be having a right move. But all these moves are possible for the active state only, right? Now halt state or inactive state can be divided into two categories as halt accept and the halt reject. If we are on the halt accept state, means we are at the final state and the string is accepted. Halt accept, halt reject is very much similar to the dead state of the DFA and FA. Okay, so here we can call it like a rejected state or a dead state, from where the machine cannot move to active state and the string is rejected. So halt reject is very much equivalent to the dead state of DFA and FA. So for these example we are going to draw or only the halt accept state for the acceptance, and for the output generation we are not using the halt reject state, but you can go with halt reject transition if you require. For the sake of simplicity we are showing only the acceptance cases. Okay, now these are the formal tuples or the formal definition for the Turing machine. As Turing machine is defined by 5 tuples, as the Q is defining the finite and non-empty set of states. This is defining the input symbols like DFA and FA and PDAs. Now Q naught is defining the initial state and Q naught is the element, one of the element of the Q set, because Q naught is also one of the state. Now this is new element or new tuple that is defining the set of tape symbols, and it is not assuming to contain the blank. So if there is nothing on the tape, we are calling it a blank symbol, but we are not saying that the tape symbols are including the blank. So tape symbols are including, we can say that, input symbols and the symbols used for the output or the symbol used for the computation. So all these symbols are representing the tape symbols. Okay, so here input symbol, union output symbol, and the symbols if we required for any computation or any check will be comprising of the tape symbols. Okay, so you will be clear with these computation symbol, output symbols once we start with the examples. So here the transition function define the mapping of a state and the tape symbol, because we can also read the tape symbol as we can move from left to right, right to left any number of times. So we may read the tape symbol as well from the present state, not only the input symbol. So here we have kept the option for the tape symbol, and we may also read a blank from the tape from the present state, and we can move to one of the state or one of the halt state, halt accept or halt reject, and we can replace the present tape symbol with any of the tape symbol, and also we can replace the present tape symbol with a blank. So we are reading from, we are moving to another state or the same state, and we are replacing the present tape symbol with any of the tape symbol or a blank, and we also need to define the direction of next read, means either we will be reading the symbol from the right or the symbol from left. Okay, or we may have the static move. Okay, static move is for the acceptance, means once we need to accept the string or to reject the string, or once we decided to move to the halt state, then we will be using this static move. So here is the example of transition, means we will be using the same example of converting the lowercase letter to uppercase letter to represent these transitions. You just note down these tuple and these formats of transitions, then we will be having an example and all these tuples will be clear to you. So we can say that each move of the machine is determined by four things, and these four things are current state, present input symbol, and symbol to write on tape in replacement of the input symbol. So here we are not having any stack, okay, but we are performing read from the tape, and by the same time we are also performing the write on the input tape. So we can read one symbol and we can replace the present tape symbol with a new symbol, and that symbol can be input symbol or the tape symbol. And we need to define the next direction, means the next symbol to be read is from left or from right, or we are moving to the halt state with a static move, okay. And by static move we mean that the machine will be moving to the inactive state and no further movement is allowed. Now let's define the transitions, how to write the transitions. So here we are taking this example. Here the finite control is at A. So like Millet-Murray machine, for one's complement, as we were on the same state and we were converting the zeros to 1 and all the ones to 0. So same approach can be used for this example here. At one state we can perform this conversion, means lowercase a can be converted to capital A, same way lowercase b can be converted to capital B on the same state. Now we need to define the next direction of move also. So here after converting this, as we are reading the string from left to right, so next direction to read the symbol from is right. Here also we will be having a right move. So here is the format of writing these transitions. So here from Q1, after reading A, from Q1 is a state from where we are reading A and we are moving to the same state Q1 and replacing the capital and the lowercase a with the capital A, and the next direction or the next symbol to be read is from the right. And same way for B, we are at Q1 and reading the symbol B and moving to the Q1 and replacing this lowercase b with the capital B, and next symbol to be read is from the right. So let's start or define these transition with the help of the Turing machine construction, so that this example or these transitions or the concept of Turing machine will be more clear to you. So let's start with the example with a sample string, this A B A. Okay, so this is the sample string on the input tape. Now the symbols are, these symbols are representing blanks, means if there is nothing on the tape we are having a blank symbol. So we are continuing with the same example. We have to convert all the input A's and B's to the capital A and B. So the output for this question must be A, B and A. So firstly we will be writing the transitions for the Turing machine, and next we will be showing the acceptance of this machine, means how the accept machine move from one state to another state and will convert these input symbol to the capital symbols or the tape symbols A and B. So now as the first symbol is null here, okay, so for every machine, for every Turing machine from initial state we need to bypass this null to move to a state from where we can start reading the input. So as we have the machine is presently pointing to the blank, so this blank, we are at this blank when the machine is when the machine starts, we are at this blank. So we have to bypass this blank. We need not to consider this blank for any computation, for any output. We just need to read this blank and start with the next state to read the next symbol right of this to the right of this blank. So here from initial state we are having input symbol as blank. We have to replace this blank with the blank, and next symbol to be read is from the right. Okay, so this is the way to define the transition. So this transition is common for all machines, means for all the machine we will be having initial state, and from the initial state we will be replacing blank with the blank, first blank, and moving to the right direction to start reading the input. Now Q1, we are at state Q1 and Q1 is pointing to the first input symbol after the blank. okay, or to the right of the blank. So now our processing can start. So this move is common for all the Turing machine, because we are considering that the input is starting with a blank and after that input is also ending with the blanks. So now this is a transition from Q0 to Q1 after replacing the first blank with blank, and next symbol to be read is from the right, and this is the format of writing the corresponding transition, and this is the corresponding transition diagram of Turing machine. Now from Q0 we are reading a blank, we are moving to the Q1 after replacing this blank with blank, and next symbol to be read is from the right. So this is the way to write the transition and this is the way to draw the transition. So okay, now from Q1 we just need, as Q1, at Q1 we are pointing to the first input symbol A, we just need to convert this A to capital A. So here are the corresponding transition, this A will be converted to capital A, and next symbol to be read is from the right of present input symbol. So next symbol we have to read from the right of the present symbol. So we have to define next direction of input read is from right. Okay, now same way from Q1 we are reading B and converting it to capital B, and next symbol to be read is from the right. So these are the corresponding transitions for this operation, as A is converted to capital A, B is converted to capital B, and the next move is right here because we are moving from left to right only. Okay, there may be the question where we need to move from right to left, left to right many times. Okay, so we will be considering those examples in later lectures. So for this lecture we are only moving from left to right, and these are the transition to convert the input symbol to the capital letter, and these are the transitions, these are the same transitions here, like from Q1 we are reading the input symbol A, moving to Q1 and replacing the lowercase a with the capital A, and the next direction is right. Now from Q1 we are reading B, and from Q1 we are moving to the Q1 only and replacing the present B with the lowercase b with capital B, and the next direction of move is right. So these are the transition corresponding to this transition diagram. Now as we are done with, if we are done with all the input symbol and all the inputs are converted to capital letters, now the tape head will be pointing to a blank. Okay, as we were having a blank before the input symbol, first input symbol, here we are having a blank after the last input symbol also. So here after reading this blank we must show the acceptance, we must move to one of the halt state. So here we will be having a static move, we need not to change this blank with any of the symbol. So we are just replacing this blank with blank and moving in the static direction, means now we need not to move either to left or to right, we are just having a static move that shows the inactive state of the machine. Now the machine is in halt state, as the machine has successfully converted all the letters to capital letter. So here we are having halt accept state, we need to draw this state with the single circle only, not with the double circle, and this shows the acceptance. Now you can read the output from the tape. Okay, so here is the corresponding transition and here is the halt state, and this is the transition from Q1 we are reading a blank and we are moving to the halt accept state, replacing blank with blank. Now the move is static, means the machine is moving from active state to inactive state after this transition, and no other read is allowed. Okay, now this is the corresponding transition table. This is very much similar to the NFA DFA's table. Here from Q0 after reading A we are performing nothing, B we are performing nothing, but for blank we are having this transition. So we have simply written this here, means from Q0 for null we are moving to Q1, replacing blank with blank, and the move is right. Next move is right. From Q1 we are having these three transition, for this is for A, so here we have this is for B, and this is defined as this, and this is for the acceptance or the halt state or to move the state to the inactive state. So this is the corresponding transition. So simple we have defined these transition in the transition table. So these three representation or these three notations are representing the same information. In exam you need not to write the transition table, or you can simply write the transition and the transition diagram, or you can go with all the tuples depending on the number of the questions, okay, or the marks for the question. Next, now we have to define the acceptance of a string. So here we are taking this as a sample string. Now like PDAs, we have to define the instantaneous description or IDs for the input string, means the states of the machine for a particular input string starting from the initial state. So here we are taking this as a sample input from Q0. From Q0 we are moving to the Q1. So we are considering this blank as a first symbol now. So after reading this blank, we are moving to the Q1 and replacing blank with blank. So here we are moving to the Q1, blank is replaced by blank, and now next symbol to be considered is this A. So next symbol to be considered is underlined here, and the symbol that we have already considered or performed the required computation is converted to the red color. Okay, now blank is considered here and it is marked with a red color here, and next symbol to be considered is this A. Now after reading this A from Q1, we are moving to the Q1 only by this transition and simply converting this A to capital A, and here is a corresponding ID. We are moving to Q1 and replacing lowercase a with capital A. Now next symbol to be considered is B here. Okay, now the tape head is pointing to this B. This B should be converted to capital B by this transition, and here is the corresponding ID. And after this, next symbol to be considered is this A, and we will be having the same transition. Now this A is converted to capital A and we are at Q1 only. Now after this we are pointing to this, the tape head is pointing to a blank after the last symbol of the input symbol. Now after this blank we need to move to the halt state by this transition by replacing this blank with blank, and we are moving to the halt state, and here is the corresponding ID. Okay, so this is the way to define a Turing machine for the given problem, and to write the transition diagram and transitions, and to write the transition table, and to show the acceptance of a string with the help of present state and the present tape symbols, and the movement from one state to another one by one. So for any question you have to perform or to write the transitions, draw the transition diagram, and to show the acceptance of at least one string. So in next lecture we will be discussing about more examples of the Turing machine construction, and how we can perform the required computation with the Turing machine will be covered in next lecture. Till then, bye and take care.